Good morning, class. Welcome to this lesson on forces and equilibrium. Today we will be able to set up a problem when we know if an object is in equilibrium. Some of the stuff I've been talking about in class, and so for some of you, you might actually get these notes and go, I knew all that. And so I really hope that's the case, that you're going to look at this and go, oh, all right, this is what we've been doing already. But I just wanted to be clear on some of these things, so that way, in case you are confused with your homework or some of your other problems, that you have a more definite understanding, because I have not specifically defined some of these things. So let's look at a case of friction first. Let's look at a case of friction. I'm probably going to do about 3 or 4 different examples here, okay? Friction. If an object is sitting on something, and I push it with 10 newtons to the right, a force of 10 newtons to the right, and it doesn't move, the force of friction is 10 newtons. If I push it with 100 newtons to the right, and it doesn't move, this is all doesn't move, then the force of friction to the left is 100 newtons. Whatever we push with, if it doesn't move, those forces are in equilibrium. Whatever is on the right is the same thing on the left. Now, some questions say something like, when an object starts to move, when an object starts to move. So we're talking at the very, very moment friction equals the pushing force. Because remember, when an object starts to move, that means it was at rest. It was at rest. And so when it's at rest, we're going to use the coefficient of static friction to solve for the problem, the coefficient of static friction. So when it starts to move, this is the maximum possible number. This is the maximum possible force that will equal the maximum possible friction. Because let's say for example, the coefficient of friction is 0.3, and let's say the normal force is 50. Well, if we do our force of friction, static, is going to be 0.3 times 50 newtons, which comes out to be 15 newtons. So that means the maximum possible static friction, I'm going to put it again, max possible static friction can only be 15. So right at that moment when we reach 15 newtons here, this force of friction will be 15 newtons here, and then we will have our maximum possible force of friction static right when it starts to move. Right when these two are equal, this is going to begin to move. Okay? And then the friction will change to kinetic friction, but that's a different question, okay? So these are two examples of forces in equilibrium for friction. Okay? Another one is constant velocity. I can't stress this enough. This constant velocity is a very, very good thing that you want to see on a lot of problems, because constant velocity means that net force is 0. And if net force is 0, whatever we have in our free body diagram, no matter what it is, tension, normal, mg, and friction, whatever, we know that if net force is 0, constant velocity, either these two are equal or these two are equal, doesn't matter, but everything is equaled out. And so we can start setting things equal to each other to solve these problems very, very quickly. Okay? This is what we mean. I'm going to bring up another term for you, terminal velocity. If you've ever gone skydiving, when people fall out of a plane and they're going down, they have gravity pulling them down. And in theory, if there was no air resistance, this person will keep speeding up and speeding up and speeding up, because their acceleration is 9.8 meters per second squared. But the reality is there's air resistance. And so at some point, air resistance or friction is going to equal gravity. So I think it's somewhere around, I could be way off with this, around 200 miles per hour that we reach terminal velocity if we're jumping out of a plane. And once again, I think I remember that, but I could be way off. So what does that mean? Even though this person is falling at constant velocity, the net force is 0. the force of friction equals the force of gravity. So whenever you see constant velocity, that's a very, very key term for you to say, okay, I'm going to have two arrows pointing in opposite directions that are going to be equal and opposite. Newton's third law. Okay? We also might have a situation where we have two forces going in two different directions. Let's say we have an object and there's a force pushing it down and to the left. And so the question will be, what is the force that will make this go at a constant velocity? And what they're really saying is, what can we do to make this net force 0? Well, these are two vectors. So that means if we combine these two vectors, our resultant will be this. Oh, I'm sorry. I totally messed that up. What is the force that will make this go at constant velocity? So if we have two vectors, we add these two vectors together to make a resultant. This is our resultant. And so the reality is this force right here will make this go constant velocity, because when these two are equal and opposite. And this one is just a combination of these two. This is not a third force. This is the combination of these two. And if we add this one in there, equal and opposite, this will go at constant velocity. Another example is an object, or like something like a boat moving through the water. So we have a boat. That is an awful boat. Moving through the water. And is going at constant velocity. Well, that means the force of gravity is balanced out by the buoyant force. I know we haven't learned about buoyant force yet, but the buoyant force of the water is pushing it up. So these two are equal and opposite. And the thrust that is pushing it forward from the propeller is balanced out by the force of friction. So everything, once again, it doesn't matter what it is, if it's going at constant velocity, all the forces are balanced. And so if we know one, we know the other. If we know one, we know the other. So that's it. Thank you.